Warm good morning to one and all. I'm Shubhangi, a research scholar from Indian Institute of Technology, Varanasi, India, and I'm here standing in front of you to talk on my paper titled "Engineered Cobalt Molybdenum Bimetallic MOF as Electrochemical Signal Transducer for Uric Acid Detection." So a little introduction from where do I hail from. So I hail from India, and in India, a very big state, which is Uttar Pradesh. And in Uttar Pradesh, I hail from Varanasi, which is the city of temples. And I'm from the laboratory of biophysio-sensors and nanobioengineering. So we all hail from the same domain of biosensors, but a quick introduction of what they are. So according to IUPAC, it is a device that transforms chemical information ranging from concentration of a specific sample component to total composition analysis into an analytically useful signal, which is called a chemical sensor. However, if the chemical sensors in which the recognition system utilizes a biochemical mechanism, it's called a biosensor. So there are primarily three components of a biosensor, where the first is the signal detector, which comprises of biorecognition elements which capture the analyte of interest. And then the signal is generated in the transduction system, of which I would only primarily discuss on the electrochemical signal transduction systems. So there is a lot of scope of research in the development of electrochemical sensors. The first is the fabrication of low-cost indigenous electrodes or solid surfaces, which could range from ITO, FTO to screen-printed electrodes and glassy carbon electrodes. The second scope is in the fabrication of novel catalytic systems and non-enzymatic systems with different approaches on surface engineering. So that could be like development of newer materials, like metal organic frameworks, which is in my case. And the third is new strategy for the signal generation, for example, multiplexing and simplifying the user interface for commercial application of those sensors. My talk would be limited to the conversion of biochemical reaction into measurable quantifiable signals using metal organic frameworks. So if I talk about the scope of the sensor development and the global biosensor market in general, so the US biosensor market is currently at $28.9 billion and is estimated to grow at a CAGR of 7.1% by the end of 2030. With the maximum proportion of electrochemical sensors in the market. So why are electrochemical sensors so famous? So they are highly sensitive and cost effective, and they have a very user-friendly approach for developing newer POCT devices. They have a miniaturization potential and have a very fast response time when compared to optical transduction systems. I'm material scientist mostly, so I work on metal organic frameworks. So metal organic frameworks are nodes of metal ions which are connected to organic linker moieties to form a 3 or 2-dimensional structure, as you can see here. So they possess advantage over any other nanomaterial for of now because of their versatility in their composition, sizes, and they have the modification of their surface does not alter the physiochemical desirable properties for sensor development. They have an enormous surface area and have a high porosity. So along with it, they have weak coordination bonds, making them good drug delivery agents as well, if you want to use them apart from their usage in sensors. So their history dates back to 1960s, where they were discovered as chemical waste components. And then in the early 2000s, they were the MOF term was coined for them, and they were started as paper-based SPF biosensor detecting systems for Zika viruses. And currently, their application is being explored for electrochemical sensors, and that too in the point of in situ MOF synthesis, which I would be focusing more on. So when I tell about in situ MOF synthesis, it is important to understand that metal organic frameworks can be synthesized through various approaches. The most common one being the solvothermal method. However, if you want to understand more on the catalytic side of their usage in sensing matrices, we need to work more on their different synthetic approaches where they are more electroactive. So I would be then focusing on the electrochemical synthesis approach of metal organic frameworks. So metal organic frameworks could be unimetal or bimetallic in nature. So bimetallic metal organic frameworks have two different metal ions in the inorganic nodes. The two different types of bimetallic MOFs could have, first being the solid solution structures, where the different metal ions occupy different lattice points within a crystal. And the second would be a core shell structure, where one metal organic framework encapsulates the other metal organic framework, forming a core shell structure. The bimetallic MOF-derived nanomaterials exhibit exposed active sites, and they have a very high stability and conductivity when compared to the monometallic counter component MOFs. So the bimetallic MOF that we have attempted is a cobalt molybdenum bimetallic MOF. So initially, we have taken a glassy carbon electrode surface that has been engineered by co-depositing it with the two metal cobalt molybdenum bimetallic MOF for the electrocatalytic oxidation of uric acid and its conversion into allantoin. So a little discussion on the significance of the analyte that we have chosen. So uric acid is a biocompound also known as 2,6,8 trihydroxypurine, and it is linked to various biophysiological pathways like purine, which is adenine and guanine metabolism and decomposition. It is an analyte of concern, being an analyte which is generally used for detecting gout, hypertension, hyperurenemia, and cardiovascular diseases, and chronic liver and renal diseases as well. So the blood glucose uric acid meter market is projected to grow at a compound annual growth rate of 11.06% from 2024 to 2031, and transitioning from 76.6 billion US dollars in 2023 to 159.64 billion dollars USD by 2031. The clinical range is stated here for blood, serum, and urine samples, which we would be focusing later. So the uric acid sensor market worldwide has large players from various countries. So why do we need another uric acid sensor, by the way? So most of the sensors that are in the market are immunometric. So the probe stability is highly compromised, and they are very expensive and have very low availability in the developing low-income countries. To eliminate the required mediators in the process is another approach that we want to take upon. So we synthesized the cobalt molybdenum MOF through the electrodeposition method by optimizing the potential and the deposition time. And we were successfully able to synthesize the bimetallic MOF, which we confirmed using various physical and electrochemical characterizations. The primarily being the FTIR studies, where we could get the stretching and bending modes of the imidazolic ring, that is the linker moiety in the MOF structure. The electrochemical behavior of the cobalt molybdenum bimetallic MOF was investigated through different routes. The first being the cyclic voltammetry method, where the bare electrode surface was when coated with the electrode deposited with the cobalt molybdenum MOF, saw an increase in charge transfer characteristics by almost 1.5 times than the bare electrode. Apart from that, a scan rate dependent study was conducted where the scan rate was varied from 10 millivolt per second to 100 millivolt per second to understand the diffusion controlled charge transfer behavior of the electrode surface. And we found a linearity in the current with the under root of the scan rate, which proven our hypothesis for diffusion controlled charge transfer with a R square of 0.91 and 0.98 for the redox process. Apart from that, a control study was also conducted where a scan rate dependent analysis was done in presence of this target analyte, that is uric acid, in a concentration of almost 10 to the power minus 4 molar, where we found out that, and again, our linear trend in the current and the under root of the scan rate study stated a diffusion control charge transfer behavior even in the presence of the target analyte. A preliminary study was conducted where the sensor probe was tested against varying concentrations of uric acid, and the preliminary results are quite promising, and we can see that there is still a scope for using the sensor probe for a wide linear range, covering the clinical range of the uric acid as well, which lies in the millimolar ranges in the human serum and blood. So our future work would be directed towards understanding the complete range of uric acid concentration that we can test it upon, for which the sensor is effective. The second thing to be done is the specificity analysis, where we would be doing more on the interference study of the particular sensor probe. And then we would integrate the proposed metrics in wearable and patch-based sensors and detection of a range of other clinically significant analytes for the developed bimetallic sensor probe. I extend my heartfelt thanks for IEEE Biosenses 2024 for providing me with the WISE Travel Grant, and also would like to thank the Ministry of Education, Government of India, for funding my research.